We can determine the electric potential of a distribution of electric charge by summing the contributions from tiny bits of electric charge in the distribution. In the limit that these bits of electric charge are infinitesimally small, this summation becomes an integration. As we have seen in similar calculations for the gravitational interaction, these infinitesimal bits of electric charge can be whatever shape is useful for the geometry of the calculation. For one-dimensional systems, we relate the infinitesimal bit of electric charge to an infinitesimal bit of length. For these systems, the point particle is the best and arguably only choice to use. A good example of such a system is the uniformly charged rigid rod. For two-dimensional systems, we relate the infinitesimal bit of charge to an infinitesimal bit of area. Common examples of constituent bits of charge are points, rods, and rings. The choice for the shape and equation for the infinitesimal bit of area depends upon the shape of the distribution of electric charge in the system. For example, a thin rod is a good shape to use when constructing a square, and a thin ring is a good shape to use when constructing a hollow tube or a disk. For three-dimensional systems, we relate the infinitesimal bit of charge to an infinitesimal bit of volume. Common examples of constituent bits of charge are points, disks, and squares. While points can be used for any geometry, disks can be used to construct solid cylinders, and squares can be used to construct cubes. The advantage of using shapes other than points is that they often simplify the calculation. This results from the fact that we are using previous solutions. For example, if we know the electric potential of a rod, we can calculate the electric potential of a square using only one integral, whereas using points requires two integrals. A similar situation occurs for three-dimensional systems. If we have already completed an integral in the solution of a previous system, there is no need to do it again. Now let's calculate the electric potential of a uniformly charged solid disk. We can model the disk as a collection of thin rings. We have already determined the equation for the electric potential of a ring, so we can apply it here. If these rings are infinitesimally small, we can use the following equation for the infinitesimal electric potential of each of the rings. In this equation, dq denotes the electric charge of each ring, the variable r denotes the radius of each ring, and the variable z is the height of position P above the center of the ring. Since the disk is a two-dimensional object, we must relate the infinitesimal bit of electric charge in each ring to the infinitesimal surface area of each ring. The density used in this relationship, denoted by the variable sigma, thus has the units of charge per area. The limits of the integration are the limits of the radii of the rings we will use to construct the disk, specifically from 0 to r. Since the disk is uniformly charged, the charge density is constant and can be taken outside the integral. The resulting final integral is straightforward. Completing the calculation gives us this result. The final step in our solution is to substitute an expression for the surface electric charge density of the disk. Next, let's calculate the electric potential of a uniformly charged hollow tube. We can model the tube as a series of stacked rings. The electric potential of a charged ring was determined previously. If these rings are infinitesimally small, we can use this equation for the infinitesimal electric potential of each ring. In this equation, dq denotes the electric charge of each ring, and the variable r denotes the radius of each ring. Since the tube is hollow, the radius of each ring is equal to the radius of the tube. Finally, the variable z denotes the distance from each ring to the position P where the electric potential is measured. Since the disk is a two-dimensional object, we must relate the infinitesimal bit of electric charge in each ring to the infinitesimal surface area of each ring. The density used in this relationship thus has units of charge per area. Substitution of this expression for the density gives us an equation for the infinitesimal bit of electric potential of each thin ring. The closest any ring in the tube can be to the position P is y. The farthest any ring can be from the position P is y plus h. Thus the limits of the integration are from y to y plus h. As before, since the charge density is constant, it can be taken outside the integral. Performing the integration gives us this expression. The final step in the calculation is to substitute for the electric charge density of the tube.